Okay, I'd like to take a look at a couple of simulations of confidence intervals. And this one, what we have over in the right-hand side here is a population distribution and a sampling distribution. Of course, the sampling distribution will be narrower because the standard error of the sampling distribution is sigma, which would be the population standard deviation divided by the square root of n. And that'll make it narrower, of course. So what I'm going to do here is just click sample, and you can see we have one sample of data. It has a spread that's not exactly, but it's more closely akin to the population from which it came. This is just one sample from that population. And then we have a confidence interval, much narrower because for our going plus or minus 2 standard errors, where we have a standard error, sigma divided by the square root of n. So that's one sample, and I'm going to sample again. And you can see I just get a different sample, and it's going to vary from sample to sample. This confidence interval, this mean and its confidence interval is a little bit lower. So I'm going to continue to sample. You can see what I get with different samples and different confidence intervals. And you can see finally here, well, not finally, but you can see we get a sample right here, and colored in red. This is a sample that does not include the mean of the true population. With a 95% confidence interval, in the long run, that's going to happen about 5% of the time. That's what a 95% confidence interval is. It says if we sample repeatedly, about 95% of the time we will have a confidence interval that includes the true population mean. And 5% of the time we will have a confidence interval that does not include the true population mean. So now I'll just select 25 at a time. You can see out of this 25 that we have 23, 92% would include the true population mean, and then 2 out of the 25 or 8% did not, and then you can keep sampling and sampling and sampling, and in the long run you ought to get closer and closer to 95%. You can see we're at 94% in this particular case. If I were to increase the confidence level, what you can see is that the width of the interval is going up, because as we move, we'll just give you numerically, if we went from 95 to 99, the confidence coefficient, you can check this out on the bottom of your t-table with the z-values, would have gone from 1.96 to 2.576. Put that down to 95. And here we'll see what happens when we increase the sample size. It's not doing as good of a job of showing that on this. You can see that the standard error of the distribution went smaller, sigma divided by the square root of n. I don't know if it's going to be as easy to see on here or not, but your confidence intervals, okay, you can see it here, are narrower when the sample sizes are larger because the sampling distribution has gotten narrower. Okay, we'll move to another confidence interval applet. And in this one, I'm going to do a test of means. I'm going to start with an exponential population, a mean of 75 and n equal to 100. Let's start off with just getting one interval at a time. So this is my one sample right here. And you can see it looks like the population. It's going to be skewed just like the population is. And then here is the mean of that one sample. Then I'm going to take another sample and it's going to plot that on here. And then another one, and then another one. And I'm going to go ahead now and plot 100 of these. And you can see over here we have all of the intervals. And of this 100 intervals, 1, 2, 3, 4, 5 did not include the true population parameter. In that first set that we did, there were 2 or 3 red ones that didn't. So in the total here, we have 93.3%, close to 95%. And the other thing you can see here is that our individual sample looked like the population skew or had a similar, but the distribution of means, the sampling distribution, begins to look like a bell curve. That, again, is due to the central limit theorem, or at least is what the central limit theorem proposes. We can do this also for proportions. I'm going to use a slightly different formulation. This isn't the exact formulation our text will use or that our formulas use. There are some formulas that are a little less biased than what we use. They're just beyond the scope of the textbook that we're using. I'm going to, again, just take one sample, and you can see that I have failure and success. Here we have it was 52% successes, even though the true population is 50 in this particular sample. And we wouldn't normally know that it was 50, but we're doing a simulation here. We know it's 50-50. In this particular sample, it was 52 to 48, and we've made a plot of that on the distribution of the proportion here. And our interval that we have does include the real population mean. So again, by the way, this pi here, some books use pi for the population proportion. I kind of like that, but most books use p, so I finally gave in. So now I'm going to take 100 samples, and you can see in this case that I have 2 of those that did not include the true population proportion. Got up here in the 60s, it looks like. And I can then sample some more and some more. And you can see that in the long run, in this case, after about 300, we had 95% of the intervals that really did cross the true population proportion, but 5% didn't. Again, that's what confidence intervals, that's what a confidence interval suggests, or what it is. In the long run, if we take many, many samples, construct a confidence interval from each of those samples, 95% of the intervals will include the true population parameter, where it's a mean or a proportion, or difference between means, difference between proportions, or correlations. We'll get to all of those later. No matter which of those statistics, 95% of the intervals will include the true parameter, and 5% will not include the true population parameter.